everyone. I hope you're having a great time at the Data Platform Virtual Summit so far. My name's Darshna, and today I will be presenting the session on the AI Gambit, considering climate change. So in terms of an agenda, we'll be covering the basics of climate AI. We'll then consider the history of development and how models have improved. And we'll be looking at whether climate AI is actually sustainable itself. And then finally, we'll be leveraging some of those open source climate resources. So let's get started. A little bit about me. My background is in neuroscience. Since my academic career, I've been working with the data science and cloud consultancy ElastiCloud, where my predominant focus has been on developing products within sustainability using AI. I'm also a Microsoft AI MVP, and I run a large Data Science London meetup group. You can find me on Twitter. There I post a lot of the content I find useful and share a lot of the community engagements I'm involved with. So before we get started, if you do have any questions throughout, please use the Q&A chat. I'll do my best to answer throughout and briefly towards the end as well. So if we consider firstly what is the climate system, we can see it's quite complex, comprising of 5 major components, starting with the atmosphere, which is essentially this upper gaseous envelope that surrounds our Earth. We have the hydrosphere, which consists of our oceans, rivers, lakes, underground water. The biosphere, which consists of living and dead organic matter. The cryosphere, which has a lot of those reflective properties, glaciers, snow cover, ice sheets, sea ice, and then the lithosphere, which is essentially that upper layer of the Earth. So without even considering any human interaction to start with, we can see the climate system itself is quite complex, with a lot of moving parts that are dynamically changing over time. So what is climate AI? So climate models typically focus on the representation of exchange of energy between the Earth and space, and that this is typically focusing on the Earth's average surface temperature. So data and machine learning are not revolutionary to climate science, as kind of technology has developed along with machine learning approaches, and our kind of urgency around understanding climate change in an attempt to kind of drive innovations around mitigation and adaptation. We have started to apply a lot of the state-of-the-art machine learning models to climate data, which has allowed us to kind of improve our insights and policies and actions thereafter as well. So if we consider a basic climate model to start with, in this scenario we are considering simply the energy coming into the Earth's atmosphere and the energy being reflected back out. So if we start with the energy coming in, we have the solar constant. Not all of that energy is absorbed, some of it is reflected, as is represented by this albedo reflection, and we multiply that by the area of the shadow, as not all points on the Earth will receive the same amount of energy. We use pi r squared to represent the area of the shadow. In terms of the energy then being reflected back out, in this scenario it's very simple. We're not considering any greenhouse gases. So we have epsilon, which in this scenario we will assume is 1, sigma, which is a constant, temperature to the power of 4, and we multiply that by the area of a sphere to represent Earth, 4 pi r squared. So we can essentially rearrange this formula so that the only unknown is the Earth's temperature. And to illustrate the point, I've put a little summary table here in which we have the solar constant for Venus, Earth and Mars, Venus being larger as it's closer to the Sun, and representatively Mars being much lower. In terms of the albedo reflection, Venus is surrounded by a lot of cloud cover, so has a higher albedo in comparison to Earth and Mars. So we plug those numbers into our equation here, and we end up with the Earth's temperature in Kelvin here. With Earth at 255, when we compare this to what the Earth's temperature is in reality, we can see we're quite a way off, and that is because we have literally stripped back all of the complexity, all of those interactions, the human interventions, etc., and we've just literally considered energy coming in and energy going back out. But this provides us with a great starting point from which we can then develop and add more data to kind of understand some of those complexities better. So we started with the bare rock model of energy coming in and energy being reflected back out. We can then add the effects of the greenhouse effect. So this accounts for the atmosphere, and some of that energy will then be absorbed by our atmospheric layer. Some of it will be reflected back out to space, and some of it will be kept within our Earth's atmosphere. We have greenhouse gases, which will also absorb some of that heat energy, but as we get to the atmospheric window, temperatures are much cooler, and reduction in kinetic energy means that a lot of that heat energy is not being absorbed, so it'll be kind of reflected back out. We have convection, so as heat rises, a lot of latent energy is dumped within higher altitudes of our atmosphere, and kind of convection processes enable that energy to be redistributed across our Earth. Then we have the geographical topology. So not every point, as we kind of explored, on the Earth will receive the same amount of energy coming in and coming out. And as we can kind of see from this little graphical representation here, the equator will receive the kind of most amount of solar energy, as represented in black here, and then less so at the kind of north and south poles. And consequently, the infrared energy that's being reflected back out follows a similar profile, but in a deficit. So we'll have kind of those, our oceans and wind forces to kind of redistribute that energy, to kind of give us an equilibrium point over a long enough period of time. And then obviously the Earth naturally rotates, so those rotational forces also need to be mathematically accounted for. So when we start to build these models, we can kind of see the complexities kind of increasing. And so what we ideally want to do in this scenario is to split our Earth up into a grid, and consider all the interactions between these different grid points, accounting for greenhouse gases, convection, geographical topology, and Earth rotational forces. In addition, we also have many different feedback loops, which add another layer of complexity to our climate models. And generally, positive feedback loops are an amplifying effect of climate change, and negative feedback loops are a stabilizing effect. So if we consider the ice albedo to start with, this is generally having an amplifying effect on climate change. So as we kind of increase our emissions, our carbon output, we're heating our atmosphere, and that's leading to our ice caps melting. So ice caps are really good at reflecting a lot of that solar energy that comes into our atmosphere, but as they kind of melt away, that ability is being diminished. So that is kind of reinforcing more temperature increases, which is leading to a further diminished reflective capability. So having a positive effect on our climate. Water vapour has both a positive and negative feedback ability. So in the sense of a positive feedback in which climate change effects are being amplified, we see again a lot of carbon being outputted into our atmosphere, that's increasing our temperature, which is leading to water to be evaporated at a quicker rate. Water vapour itself is a greenhouse gas, which is then again reinforcing further kind of temperature increases within our atmosphere. Clouds, they're quite a complex area of climate science and can have both stabilising and amplifying effects depending on where the type of clouds and where they are within altitude. So the higher clouds, cirrus clouds, are generally quite thin, they occur at high altitudes, and they have quite a strong warming effect because they're absorbing a lot of that infrared energy. Whereas lower clouds, cumulus and stratus clouds, have a much more stabilising effect. As they're thicker, the particles are more in line with visible light and have strong reflective capabilities, so they are providing a cooling effect. Then we have aerosols. So aerosols occur naturally from volcanic eruptions, sea salt, desert dust, but also from burning coal. So when we burn coal, we end up with sulfur dioxide being released. With a few weeks in our atmosphere, that turns into sulfuric acid. And those particles are great at kind of reflecting a lot of that solar energy back into space. So whilst they have a cooling effect, there are some ambiguities surrounding the kind of intensity to which that cooling effect occurs in comparison to the warming effects of carbon, methane, and freons that we see within our atmosphere. And then we have the carbon cycle, and the carbon cycle, quite simply, is a representation of carbon between our atmosphere and Earth, ocean, and land, essentially. So our oceans are a large carbon reservoir and have typically had a stabilising effect, predominantly up until now. As we've kind of pumped more carbon into our atmosphere, it's kind of absorbed. Our oceans have absorbed all that carbon output. But there are kind of arguments that there will be a saturation point in which it can then turn into a positive feedback loop. And the land, again, another huge carbon reservoir, is quite interesting. We see a different carbon profile, carbon fluctuation profile according to the northern and southern hemisphere. So the northern hemisphere of our Earth has a lot of plants, a lot of land and trees, in comparison to the southern. So we'll see those seasonal fluctuations of carbon according to spring and summer versus autumn and winter, where things are dying or dead and the carbon absorption capability is diminished. As we've kind of modernised our cities, expanded our cities, repurposed land for different agricultural growing patterns, we can kind of see more fluctuations in the northern hemisphere's carbon profile. But that kind of combined with the increased warming that we see with climate change has led to some increasing in growing cycles, which has kind of diminished those increasing fluctuations over time. So all of these kind of really complex feedback loops are ultimately affecting our climate sensitivity, which climate scientists essentially define as the change in temperature as a result of doubling CO2. So we've kind of considered a lot of the basics of climate science, and I just wanted to highlight a few resources that I found useful. If you are interested, I urge you to have a look further at this course, our course, which covers a lot of what I've spoken about in terms of the physics, chemistry, geology of energy systems, but then goes one step further to consider the human impact that societies have on climate change and how economics feeds into that too. If you're interested in further understanding some of the mathematical modelling, this is also a great book and goes into that in a lot more detail. And of course, there are tons and tons of open source packages, open source data sources. So this is a link to a GitHub profile that essentially lists a lot of great sources of models and Python packages and data sources. So one here that I've particularly enjoyed using is the Climate Laboratory, which is essentially a book that goes through all the basics of climate science. And there is also an accompanying Python package called ClimLab, which allows you to use some of the out-of-the-box climate models and experiment with changing different parameters there. So now we've kind of considered the basics of climate science, I would actually like to look at the history of development, essentially, and how we've kind of gone and progressed in terms of scenario modelling. So scenario modelling was initially used in the military and in gaming, and was started to be used in business in the 1960s. So the first kind of, scenario model on climate change started in 1997 when the Special Economic Report on Emission Scenario was developed. That took 3 years to develop, and then in 2001 that report was enabled to be used within climate modelling. And then by the time the Intergovernmental Panel on Climate Change was able to produce the impact report, it was 2007. So we can kind of see those very early scenario models followed a very linear path, and took almost a decade to produce, which in that time a lot of data patterns can change, a lot of technology advances, so we're almost out of date to really have a benefit in terms of understanding the impacts that needed to be made in terms of looking at our policies and innovations that needed to be made. What we have nowadays is a much more parallel path, and thanks to some great industry professionals and climate scientists who developed the representative concentration pathways, which essentially provide a trajectory of possible outcomes rather than trying to predict specifically the effects of those greenhouse gases on our atmosphere. We're able to use those parallel pathways within climate scenario modelling, within socioeconomic modelling, to really be able to output effective impact assessments in a timely fashion. So looking at those representative concentration pathways in a bit more detail, I've just pulled up this figure here, which is from the 5th IPCC report. And across the x-axis we have time, and across the y-axis we have CO2 equivalent in parts per million. So all of those greenhouse gases are, in this instance, converted to their CO2 equivalent. So we have 4 representative concentration pathways that we're focusing on here. And here we'll start with the red line, which is RCP 8.5 and commonly referred to as the business as usual RCP. So this is if we do nothing and we continue to emit the same amount of carbons without the necessary changes that are required. By 2100 we can see some phenomenal increases in carbon output, but also here in temperature, which will lead to some devastating living conditions and crashes of vital ecosystems that we rely on. More optimistically, we have RCP 2.5, which we've actually probably missed the boat on a little bit, but we do realistically can consider RCP 4.5 and 6 here, in which we'll still see some effects of climate change in terms of temperature, and we can kind of see here that this decade is critical to where we end up kind of in the decades to come. So, in terms of where innovations are required and kind of climate AI can help further, we're just seeing here essentially the world greenhouse gas emissions in 2016 according to sector. So we can see transportation, electricity, heat, and infrastructure of buildings, fuel combustion, and manufacturing and construction are really where the bulk of our emissions are focused. We also have agriculture and land use in terms of forestry to also consider. So that is where we can kind of look one step further at how AI is being used to fight climate change in terms of mitigation and adaptation. So we can use AI obviously to understand our climate systems better, but we can also use it to predict energy demand. So there's across Europe and the UK, there is a huge energy crisis at the minute where it's becoming extremely expensive to kind of consume energy. So being able to predict that consumer demand is obviously a great thing. We can use AI to discover new materials, so whether that's solar fuels, learning how we can develop new kind of materials to absorb carbon more effectively can also be a great application. We can use AI to optimize our transport. So we are using the shortest routes with the least amount of emissions. We can lower the barrier to electrical vehicle adoption. We can implement IoT devices within our buildings, so we can smartly monitor and manage our buildings so that we're not heating and lighting buildings unnecessarily. We can optimize our supply chains. Obviously, as kind of climate disasters and extreme weather conditions are anticipated, we'd need to understand how that affects our supply chains so that vital food supplies and things can get to people where necessary. We can implement precision agriculture at scale. So a lot of pesticides are used within agriculture at the moment, and that is kind of down to also kind of down to how we're repetitively using the same lands for growing crops. So if we can implement AI to understand growing patterns, we can maybe implement more intelligent rotation of agricultural growing practices. And then we have deforestation. So Greenpeace actually used this form of AI recently this year. So in the UK, peatlands are a large carbon reservoir, accounting for around 3 billion tonnes of carbon. And the UK government last year made it illegal for peatlands with a depth of more than 40 centimetres to be burnt, essentially. However, Greenpeace have been looking at some NASA satellite imagery which was able to detect illegal forestry of those peatlands, which obviously has devastating effects for that carbon reservoir that essentially equates to the same amount of forest that is in UK, France and Germany combined. So that can have some interesting applications to try and mitigate further damage to our environments. And then we have advertising. So this is around changing cultural patterns and consumer activity through education, essentially. So the second kind of visual representation here is essentially showing the EU-funded projects that are using AI to address climate change. And we can kind of see, obviously, a lot is still going into natural sciences, but we also have a lot in engineering and technology and social sciences as well, which is great to see. So we've spoken a lot around the kind of positives of applying AI within climate science. But there's also the flip side of the coin to consider in this scenario as well. And just to represent this point, I've kind of called on a few facts that have recently been referenced in some papers and different media outlets as well. So firstly, considering data centres. So data centres are forecasted to account for 8% of global electricity demand by 2030, which is a huge amount. So yes, AI has a lot of great important applications, but it also comes at a cost. And again, representing that in another Nature paper, the technology ecosystem has been illustrated to be on par with the aviation industry in terms of its carbon emissions. And the Economist and Forbes have described data as the new oil. So yes, there is huge amounts of data available in our world today, which is great in terms of driving insights and action once it has been refined into a usable format. But as I mentioned, that comes at a cost, and that cost and compute power is also attributed with emissions. So we need to do that in a responsible way. If you are kind of interested in exploring the flip side as well as the positive applications of AI within climate science, this is a great paper, which is actually the inspiration for this talk. And it kind of goes into how AI is essentially being used to understand climate change and combating climate crisis effectively. It also then goes on to look at exactly that, the compute and emissions costs that are associated with developing AI, but also some of the ethical implications. So, for example, if we are looking to develop our electrical vehicle infrastructure, the data biases that may be present within the training data are things that we need to consider carefully, as electrical vehicle adoption is more likely to be an occurrence within affluent areas of society, and there are some natural biases there. And then finally, they go on to put forward several recommendations around how we can go on to develop AI for climate change and climate understanding in a much more responsible way, which I will go on to touch on in a moment. So AI development is set to grow by 44% by 2025, but it's expected that there will be a diminishing returns where the additional costs does not reflect a return on investment, essentially. So here, to represent this a bit further, is a visual taken from The Economist, and essentially we have time across the bottom with petaflop per second on the y-axis. And as you can see, as time has gone on, our algorithms have kind of increased in complexity, but not with necessarily increases in performance, which are important considerations to make. So how can we go on to develop AI in a more sustainable way? So one of the initial kind of recommendations would be to move a lot of compute intensive processes to the cloud. A lot of cloud providers these days are using a lot of renewable energy. They have customized hardware to ensure effective cooling and heating, and use of data center infrastructure. So moving to the cloud is the first step. The Green Software Foundation, along with Microsoft, have put forward the principles of sustainable software engineering, which initially obviously focus on the education around understanding how software development is essentially using carbon and electricity. But then it also goes on to suggest several practice changes that can help us develop software in a much more sustainable way. So considering the carbon intensity of the region in which software is being developed is a great consideration to make initially. So ensuring your resources are in relevant low carbon intensity regions, ensuring that the network has been kind of efficiently optimized. So the distance that data needs to travel over networks can be minimized. Demand shaping, so moving away from this always on type architecture, and optimization, so essentially moving more towards a serverless type architecture. So this is great from kind of a holistic point of view, but focusing more on AI specific considerations, we kind of look at data quality regularly to improve the performance of our models. So that is also something to consider. It's not necessarily the most amount of data, but data that has the most correlational value to what we're trying to predict. That might be an important consideration to make. And likewise, it's not necessarily the most complex algorithm that has the best performance, but it's often the models that have the best data quality. So if we've got large amounts of missing data, can we use alternative sources? Can we feature engineer? Just spend a little bit more time doing the relevant quality assurance checks and exploration to ensure that before we apply our compute intensive algorithms, that we have an adequate foundation to build those models on. So precision, understanding uncertainties. So again, we're often chasing percentage values in terms of better performance, but that's not always justified in terms of cost saving or profit making, or even in this case, the emissions cost associated with that development work. So they should regularly be kind of considered within the development process, not just after, but probably before and even during as well. Having relevant check marks within development life cycles, and making sure it's kind of a distributed responsibility rather than falling down to one person. And incentivizing collaboration and open source. So often within a lot of development practices, things can be reused, and if they're shared, and if they're kind of kept in an appropriate manner, and often we can use sources that are already there in the open source community as well. So that is also an important consideration to make. So just to kind of illustrate the point of some of those considerations to make, here we have a representation of the NLP GPT-3 model being trained in different Azure regions. So everything else is kept the same. The training hours, the GPU, the cloud provider is the same. It's just literally the region in which the model has been trained that has changed. So we can see there's quite a substantial difference between training this model in South Africa, where the associated carbon emissions are 942,330 kilograms versus 93,000 kilograms in France. So obviously France is dependent on a lot of nuclear energy, which there are a lot of ethical issues surrounding the kind of workforce in Africa that was used to mine a lot of those minerals that were required to develop those nuclear forms of energy. So that's not necessarily a completely sustainable kind of outlook, but from just purely the environmental point of view, it is a lot more kind of cost effective to train this model in France versus an Azure resource in South Africa. So what is some of the data that we'd look to collect during the training phase to really assess the greenhouse gas emissions related to the development of different ML models. So we can look at firstly the number of experiments. We can look at the number of floating point operations, hardware information such as CPU and GPU, the experiment start and end time, the energy grid region, so ensuring that we're training models in the lowest intensity, carbon intensity grid regions, and memory usage. So in terms of kind of tools that can help us assess some of this further, Microsoft have their sustainability calculator, which allows us to look at the emissions by resource. So we have compute, storage, analysis services, networking, all kind of considered there. We can look at the emissions over time and by geographical region, as well as some great comparative metrics there too. In terms of kind of understanding how further the recommendations of developing AI more sustainably, some of the things that we can kind of look at is to essentially develop world-leading observatories so that kind of people have resources that they can go to, rather than everybody using satellite data and starting from scratch. There are resources that allow us to leverage those sources in a much more kind of accessible way. We can develop standards of quality. So what is a good practice of developing AI in a more sustainable way, incentivize collaboration and ethical auditing, which isn't something we really see done at a software level. We can encourage carbon assessments to occur before development work commences, and then disclose the carbon assessment metrics after, just to provide people with a benchmark essentially to start understanding what is good sustainable AI development. We can incentivize diverse research agendas. So a lot of competitions, Kaggle is a great example, in which the models that perform the best and receive and reach the higher levels of accuracy are often kind of the ones that win competitions and things like that, and are kind of praised. So in terms of changing that cultural narrative, so that we're also focusing on not only the best performing model, but the one that is the most energy efficient, would be a great thing to see. And then obviously assessing the carbon footprints of commonly used models and frameworks that and platforms that we commonly use within AI development, such as PyTorch and TensorFlow, would be a great thing to increase awareness and education around AI development. So in terms of leveraging open source climate models, there are tons out there, but just to highlight a few, the Microsoft Planetary Computer is a great set of APIs that allow us to access satellite data, weather data, biodiversity data in a really accessible way. So that's a great place to get started, and there are quite a few good examples on the AI for Earth initiative about how a lot of those APIs can be leveraged. There is the RCP database, in which you can get those emissions forecasts up to 2100 out of the box. And then there is Climate Change AI, which is a great website which essentially aims to bridge the intersection between climate research and machine learning. So you can see a lot of the great research outputs of climate science modelling using AI tools there. So I just wanted to illustrate in some of the areas within our own products in which we've kind of used a lot of those open source tools. So the RCP database is one of them. So this Sustainability Studio is essentially a tool that outputs an ESG score for each company of the FTSE 100, and it does that using a range of different data sources. So we use sustainability reports, finance data, social data, a lot of environment data and news feeds. So we can kind of use some semi-automated processes to mine a lot of those ESG metrics. We pre-process that, apply a lot of weights and normalization processes to output those ESG scores and forecast into the future. But what we've actually used the RCP database for is to output some revenue at risk models. So looking at those emission scenarios, looking at flooding, cyclone risk, drought risk, a lot of that, we can understand where certain companies are have a large proportion of their revenue at risk. And then we've also used a lot of open source news data as well to output controversies, as sustainability reports are naturally quite biased. So a lot of use of open source data and tools there as well. So that can all be accessed via Power BI into a report that looks quite similar to this. So here we're looking at the banking industry for the year 2026, and we can see things like the average emissions according to GDP by country, the number of cyclones by GDP in country, flood risk by GDP in country, with some great summary tables there as well. So just to kind of bring together a lot of what we've talked around in terms of basic climate science, the applications of the positive applications of climate models and machine learning models that kind of are focused on developing tools for mitigation and adaptation, as well as just making sure that we're cognizant of the emissions that are being generated as a result of development. I wanted to focus on one demo, and this demo is predicting, using some open source data to predict wildfires in California for the next month ahead. I thought this would be, I was kind of motivated to focus on this particular scenario, just given some of the extreme weather conditions we've seen here in the UK, in which we clearly don't have the infrastructure to essentially go about our daily lives. And given some of the record-breaking temperatures we've seen here this summer, it's got me thinking around, well, if we were able to predict wildfires specifically as a result of increased temperatures, which are going to be more and more likely, how could we use that to improve the infrastructure that we have? So why focus on this? So obviously supply chains would be disrupted as wildfire prevalence increases. There is obviously a great risk to public safety. So ensuring that we have relevant resources and can provision relevant emergency service personnel to deal with such type of disasters and weather events is obviously a great thing. As in certain areas, particularly California, home insurance will be affected by increasing climate change, and just generally understanding the patterns of wildfires and the prevalence in the kind of ongoing climate change patterns that we see is obviously a good thing to understand as well. So we'll look at the emissions of a basic model and then go on to consider if we were to increase the complexity of this model, is further development essentially justified? So this is the data source that I have used. It is from the US Department of Agriculture, and all the data can be accessed here. So if you want to start on your own kind of machine learning modelling, there are a lot of government resources and data sets that are available out there. So I've read this data in, and then I've started with some basic exploratory data analysis and cleaning. So here we're considering around 1.8 million wildfires with around 38 columns in terms of features to help us start beginning to navigate whether we can predict wildfires for the next month ahead. So I've looked out of those columns initially, how many nulls are there. So we can see for things like the number of wildfires, that we don't have any missing data, which is great, and also the state, so that we have good data on the location in terms of longitude, latitude, and state. The discovery date is also not missing. So I've kind of filtered out those relevant columns just to start some basic cleaning and exploratory analysis. So here I'm just pulling out those longitude and latitude and just doing a bit of cleaning to the data types, expanding out some of the features that we can generate from the date, such as the month, the day of the week, etc. So then we begin initially looking at the number of wildfires per year. So we can kind of see it's not a strict linear increase. 2006 is probably where the most number of wildfires are recorded in the US here. But there is that general upward trajectory as well. So then we've gone on to look at the fire size, which, as we can kind of see here, has quite a small mean, but a huge amount of outliers. So looking at that in terms of a more tabular form, we can see the average fire size falls somewhere between 30 and 150 or so. So there are quite a lot of outliers that go far beyond that range. Causes of wildfires generally fall in the categories of debris burning, arson, and lightning. Is arson more likely on the weekend? It would seem so, just marginally. The number of wildfires by state, and as expected, California has the most amount of wildfires. So here we've gone on to explore whether the causes of the wildfires in California differ. So we have debris burning, arson, lightning equipment use, and then still a large portion that's actually miscellaneous. So we've gone on to do a little bit more geospatial analysis, which I had some trouble rendering out the visuals in the Jupyter Notebook, so I won't cover in too much depth here. But what is probably a more interesting point is that we can use GeoPandas to essentially create the point geometry that is needed to do the spatial joins should we want to start incorporating any weather data here for further analysis. So that would be a good point for that. So in terms of starting to build out the data set to predict the number of wildfires for the year ahead, I've just taken and subsetted out the California data, and then I've started to aggregate here the other features according to month and year. So we've taken the number of fires per year, the fire size, we've taken the average, the min, max per year, per month, and then we've gone on to create some lag features. So here we've created the feature for the previous year's total fires, so we can join that back to the original data set and then later drop the total fires, as that's some data that we wouldn't have at the point of predicting. And then we create the lead feature, so we want to predict the number of fires for the next month, so we're creating a lead feature here. So before applying any algorithms, we want to explore whether we have correlational power with what we're trying to predict. So we're trying to predict the next month of the number of fires for the next month ahead, and we can kind of see there are some weak to strong correlations with a lot of the features we have, none that are particularly light, so that's definitely a good sign. Some of the strong ones we would remove, so the number of total fires for the current month we wouldn't have. Likewise for the current year we wouldn't have either, so they should be removed prior to modelling. So here we have data for 2003 to 2015, and we can kind of see, as a result of all of the aggregating that we've been doing, we've gone from millions of rows to just 275 rows. So quite a small data set that we're looking at here. We're doing the relevant test train split. So we are applying the algorithm on 70% of the data to learn those patterns as to the number of fires per month, and then we're testing on the remaining 30%. So I've started emissions tracking using this code carbon package, which allows us to look at GPU intensive compute that's being used. In this case, we're just applying a gradient boosted regressor across a very small set of data. So the actual energy used as a result is very, very small and negligible, as we can kind of see here. But should we want to then increase the number of experiments or the data, that could well increase as well. So we should consider whether that is justified. So if we test the model performance, we look at the R-squared here, the model's probably overfit a little bit as a result of those lag features and the small data set that we have. So R-squared ranges from 0 to 1, with good performance being between 0.7 and 0.9. We can explain the variance to 0.99, which is great. So we might want to do some further post-analysis on those features, and the mean absolute error is 9.6. So we can predict the number of fires for the month ahead using this model for California to 9, give or take, essentially. So if we were to kind of consider some additional improvements, we might want to include weather data, climate models, additional demographic or census features. We might even want to, if we wanted to explore further beyond California and consider global wildfires, we might want to start considering other algorithms that are more complex, and we might want to tune those hyperparameters as well for those more complex algorithms. So all of this is more compute, which is more emissions and more nature cost. So is it justified? It depends obviously on our use case. If the same model was going to be used for all of these different applications, then maybe, but there needs to be probably some further quantitative analysis done there. So that kind of brings me to the end of my talk. I hope you enjoyed it. Thank you very much.